Hi, welcome to this lecture of two-phase flow. My name is Mingchang Li. I am currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this lecture for the NTHU OpenCourseWare project. The topic of today's lecture is an introduction to the basics of pool boiling. Some figure contents of these lecture slides are selected from these three reference books. Besides the main textbook for this course, written by Professor Carey, the other two references are classical textbooks for general heat transfer. There is one chapter in each book illustrating important basics of boiling and condensation heat transfer. For people who are not familiar with this subject, but would like to quickly get a broader overview, it is highly recommended to study that chapter in any of those heat transfer textbooks. This video shows a saturated boiling process of water at 1 atm on a heating wire. Boiling is associated with the transformation of liquid to vapor at a solid to liquid interface due to convection heat transfer from the solid. Agitation of the liquid by vapor bubbles is one mechanism that provides large heat flux at low to moderate surface to fluid temperature differences. The nature of the requirement in latent heat during a phase change process also enables large heat transfer with small temperature gradient. Since boiling is a form of convective heat transfer, it is intuitive that the boiling heat flux from a solid surface to the surrounding fluid can be expressed by Newton's law of cooling. Note that the temperature difference in this case is usually defined as the excess temperature, where Ts is the surface temperature of the solid and Tsat is the saturation temperature of the fluid under current condition. In general, there are two types of boiling processes. The pool boiling refers to a boiling process in the absence of bulk fluid motion that is usually driven by external sources, such as pumps. The fluid motion in pool boiling is basically due to the buoyancy force and the agitation of fluids by the movements of vapor bubbles. In contrast, in a flow boiling process, the fluid motion is mainly due to a directed bulk motion in conjunction with the buoyancy effects and the bubble-to-liquid interactions. On the other hand, depending on the condition of the surrounding liquid, boiling can also be classified as saturated boiling or subcooled boiling. Saturated boiling is the condition for boiling in a liquid at the saturation temperature. In subcooled boiling, the liquid temperature is below the saturation temperature at the current pressure. This video here shows a subcooled boiling process of water. As can be seen, the bubble forms on the surface of the heating wire and collapses rapidly. Upon the point that the top portion of the vapor bubble is beyond the thermal boundary layer near the heating wire, the vapor bubble is in contact with the subcooled liquid. Heat is transferred from the vapor bubble to the cold liquid through the interface. Therefore, the vapor bubble shrinks and quickly disappeared. Boiling and bubble-induced flow in this case is confined near to the heated surface. Note that this phenomena is associated with the evaporation cycle we discussed previously in Chapter 7. The boiling curve reveals a range of conditions associated with saturated pool boiling. The vertical axis is the heat flux from the heated surface to the working fluid, and the horizontal axis is the excess temperature as defined previously. It should be noted that these numbers may change corresponding to the thermophysical properties of the fluid, but the trend is basically the same for most fluids. The boiling curve shown here is typically for water at atmospheric pressure, which is based on the pioneering experimental work by Professor Nukiyama. From the boiling curve, there are 4 stages for the boiling process: natural convection with mostly single liquid phase, nucleate boiling, transition boiling, and film boiling. Hereafter, we will use the Nukiyama's boiling curve of water for illustration. In the beginning of the boiling process, there is almost no noticeable vapor bubble. Therefore, in this first stage of pour boiling, the fluid motion and the associated heat transfer is mainly due to the buoyancy effect, or simply called natural convection. When the excess temperature is increased to about 5 degrees C, the onset of nucleate boiling could be observed. Note that the liquid water near to the heating wire is superheated and is in the metastable condition as we previously discussed in lectures 6 and 7. After the onset of nucleate boiling, the formation of bubbles increases with increasing the excess temperature and therefore the number of active sites for nucleation. The figure on the right is a reminder for the results derived by Schiff's model that was discussed in lecture 7. This regime can be further divided into 2 stages: the nucleation boiling with isolated vapor bubbles, or jet and columns of vapor bubbles if the excess temperature is further increased. In the first stage of nucleate boiling, isolated bubbles are formed on the heated surface, growing and then departed from the surface. The bubble after separated from the heated surface may shrink and collapse depending on the condition of the surrounding liquid, as we have previously discussed. The vacant sites on the heated surface left behind the bubble is refilled with liquid in the vicinity and is heated to form vapor bubble. This cycle repeats and the frequency increases with increasing the excess temperature. Then, the rate and numbers of bubble formation gradually become large enough, so continuous vapor columns and jets are formed on top of the heated surface at active nucleation sites. The strong movement of the vapor column towards the opposite direction of gravity induces rapid convective heat transfer. Owing to the strong fluid motion and liquid contact and evaporation on the hot surface, the nucleate boiling heat flux increases rapidly with increasing the excess temperature. As shown in the boiling curve, the boiling heat flux in this regime can be on the order of several hundreds of kilowatts per square meter. However, as the fraction of the surface being covered and occupied by vapor bubble increases, it is getting difficult for liquid to reach the hot surface. In consequence, the boiling heat flux increases at a lower rate with further increasing the excess temperature and eventually reaches a maximum limit. The heat flux at the point of its maximum value in nucleate boiling is called the critical heat flux. For water at atmospheric pressure, this point corresponds to the excess temperature of approximately 30 degrees C, and the critical heat flux is nearly 1 megawatt per square meter. According to the Newton's law of cooling, the convective heat transfer coefficient is on the order of 10 kilowatt per square meter Kelvin. Therefore, nucleate boiling is the most desirable mode for boiling heat transfer in practice. However, it should be noted that any attempt of increasing the heat flux beyond the critical heat flux point will cause a sudden jump of the excess temperature to the point that most materials cannot withstand and will be severely damaged or even burn out. In fact, this was observed in Nukiyama's experiment in 1934. While nichrome wire was firstly used as the heating element. To attain the boiling curve beyond this point, he replaced the heating wire with platinum having the melting point of 2000 Kelvin. On the other hand, if the heating surface temperature can be precisely controlled, the transition from nucleate boiling to film boiling could be observed. This was demonstrated by Joule and Muller in 1937. In this regime, the bubble formation is so rapid that the vapor blankets begin to form on the heating surface. Due to the much lower thermal conductivity of vapor comparing to liquid, the heat flux drops rapidly with increasing the surface temperature, since those vapor blankets block the liquid from contact with the heated surface. The last regime is film boiling. As indicated by its name, the heating surface is completely covered by a continuous vapor film. Experimentally, this regime can be observed by reducing the heat flux following the cooling curve, and the excess temperature decreases correspondingly. The heat flux reaches a minimum value at the point called the Leidenfrost point. In this regime, the heat transfer from the hot surface to the surrounding liquid is mainly a combination of convection and radiation through the vapor film. Therefore, in the heating power-controlled boiling experiment, decreasing heat flux decreases the excess temperature, as shown by the cooling curve. With decreasing the heat flux further below the Leidenfrost point, a sudden drop of the excess temperature to the nucleation boiling regime was observed. On the other hand, increasing the excess temperature beyond the Leidenfrost point leads to gradually increased heat transfer. This is mainly caused by the increased radiation as a result of the increased temperature difference across the vapor film. However, it should be reminded again, in practice, the operation of boiling near the critical heat flux point is avoided, since it is easily to be thermally out of control. Precision control of temperature to attain the transition boiling is not only difficult, but also impractical for most applications, since the heat flux actually decreases with increasing the excess temperature. Due to its complexity, deriving theoretical relations for predicting the heat transfer with boiling is extremely difficult. In practice, empirical or semi-empirical correlations or models are better approaches for evaluating the heat transfer associated with boiling or condensation. Thermophysical properties of the fluid and the heating conditions should be included in such kind of correlations. To make the correlation have more physical meanings, it is important to systematically investigate the key parameters prior to the development of relations. The analysis of the boiling convection process involves the following thermophysical properties: the excess temperature, density, viscosity, thermal conductivity, specific heat and latent heat of the fluids, as well as surface tension and characteristic length of the interface, and the gravity. In total, there are 10 variables under consideration, with 5 dimensions for temperature, mass, length, time, and thermal energy in Joule. Note that Joule is needed for the basic dimension here, since we have included the latent heat. Therefore, based on the Buckingham Pi theorem, 5 dimensionless groups are expected. With a standard analysis, it can be shown that a set of these 5 dimensionless groups are formed, namely the Nusselt number, the Jacob number, the Prandtl number, the Bond number, and a parameter that resembles a similar definition as the Grashof number. On this basis, Numerous correlations for the boiling heat transfer have been proposed. Here we list some classical relations for illustration purpose. The first one is the correlation for the nucleate boiling heat flux proposed by Rational in 1952. Correlations developed by Zuber in 1958 for critical heat flux and the minimum heat flux corresponds to the Lennard-Frost point are shown as follows. It should be noted that, in addition to those dimensionless variables discussed in the previous slide, the shape, orientation, and the properties of the solid surface should also be included in the correlation to reflect the conditions more precisely. In the cases of film boiling on a horizontal cylinder or sphere surface, Bromley proposed this set of correlations in 1950. Noted that the properties of vapor are usually evaluated at the film temperature. The radiation effect should also be included for a more accurate estimation of the heat transfer across the vapor film. In this lecture, we introduced the typical boiling curve, the characteristics of each regime, and the basic concept of analyzing the boiling heat transfer. It should be noted that the mechanisms and the characteristics of heat transfer associated with condensation process are somewhat similar to the boiling process, but in a reverse manner. Information regarding the condensation heat transfer, especially film condensation, can be found in the reference books. We will discuss about the analysis for both boiling and condensation processes in more details in the following lectures.